Hey, so I'm Dr. Matt Turner with ECET at Purdue University in New Albany, and you're watching another video lecture series for ECET 273, our course in modern energy systems. This video that you're watching is the second part in a two-part series on end loads, which are the devices connected to the electric grid. And these are the devices that really are using electricity to do useful work. You may recall from several modules ago, Module 1, that the U.S. electric power system delivers voltage and current to consumers using three separate phases. So it's not a single voltage source. There's actually three voltage sources in the system. And if we take one of the voltage sources as the reference, the other two have a phase shift of 120 degrees relative to that reference voltage. So we say we have three phases with a phase shift of 120 degrees phase separation. In this section on single and multi-phase loads, we're going to look more closely at the application of both single-phase and three-phase systems. So in the United States three-phase system, a minimum of three conductors are always used, and as a consequence, you'll usually observe when looking at the system that power equipment on the distribution and transmission levels, they are arranged in multiples of three. So here I've got a picture of a standard utility pole. This is such that you might find in a parking lot, in a neighborhood, feeding some customers, whether those are residential customers or whether those are commercial customers. But this is a pretty standard utility pole. This one's actually three independent single-phase transformers, each of these transformers being rated to an apparent power of 37.5 kVA. In previous lectures, you learned the difference between real power or true power and apparent power, and we said that utility equipment is rated for apparent power because it's got to handle the current, right? So we look at this and we see on the outside of this transformer can that it says 37.5 kVA, showing that that single-phase transformer is rated for that much apparent power. Each of these transformers in this utility, or on this utility pole rather, is connected to a different phase of the generation supply, and therefore the voltage current relationships in these transformers, I've got them highlighted in different colors, blue, red, and green. They're going to be represented by the phase diagram shown here. So arbitrarily with this one, we're taking blue as the reference phase. So it's got a zero phase shift, and then we notice that red has 240 degrees of phase shift on this diagram, and green has 120 degrees of phase shift on this diagram. We could have easily said that red has negative 120 degree phase shift too. That would have been an appropriate way to describe that, negative 120 degrees and 240 degrees being an equivalent angular rotation. In three-phase systems, some load devices are actually going to connect to all three phases simultaneously. These are called three-phase loads, and the most prominent example are large industrial motors. I struggle to actually even think of another example, but there are a lot of large industrial motors that will occupy all three phases of a three-phase power supply simultaneously. Other loads, single-phase loads, are only going to use one phase at a time. These are the majority of the loads connected in residential settings and usually in commercial settings. So three-phase loads, usually industrial devices, single-phase loads, commercial and residential. A three-phase transformer bank, just for your information, can be composed of three separate single-phase transformers. That's fine. A lot of times, however, you will see those transformers packaged together in one big element, one big mechanical element, and you'll get a three-phase transformer. It's just one big box. So if you look out there and you say, I thought there'd always be three transformers, that's not always the case, because a lot of times these internally are just packaged together. But there still are three phases in play there. Here we have some utility poles, but in this case they're carrying 6 wires actually. And the reason that there are 6 is because there's 2, if you look closely, there are 2 wires for each of the distribution phases. The phases are held separate from one another and from the utility pole, if you look here, by large ceramic insulators. So I've got this spanning structure here, and these ceramic insulators isolate these distribution lines from the spanning structure, and you'll notice that there is a spacing between these two lines, these two lines, and these two lines. And the spacing of those three phases is chosen based on the voltage level. Higher voltages are going to need larger spacing to reduce the possibility of electrical arcing, whereas if we look at a single phase, wires of the same phase can be co-located on these same insulators since their voltage difference is zero, right? These are at the same voltage. Now, despite the fact that these are at the same magnitude of voltage, there is a phase difference, so there is a voltage difference between those. So if I were to do a Kirchhoff's voltage law between these 2 points, 0 volts. If I were to do a Kirchhoff voltage law between these 2 points, it's a non-zero voltage, so there is a voltage difference between those wires. So you'll always see bundled wires in multiples of 3, right? 2, 4, 6, 3, 6, 9, etc. I said that there were only 6 wires in this. You may notice that on these poles there's actually some more wires. We'll talk about what those kind of smaller, harder to see wires are later on in the lecture, but I just wanted to show a couple examples of the manifestation of three-phase utility equipment on the system. So we've got some, transformer cans, some wire bundles, and throughout the rest of the class this theme of 3 will actually show up fairly often. So here we have a 120 volt voltage source, which is going to represent the voltage output of one of these transformers. In this case, we're kind of indicating that it would be a step-down transformer representing the voltage being delivered to a residential customer, 120 volts AC. We see that there are 2 loads connected in parallel, and we've decided to represent these loads instead of in terms of the resistances. We've decided to represent the load in terms of their real power consumption in kilowatts. If we are the engineers responsible from running a wire from this step-down transformer, which has been provided by the utility, to these 10 kilowatt parallel connected loads, what we're primarily concerned with is how much current is going to flow through this wire, right? We need to size that wire appropriate for how much current will be drawn by the load. And how big of a wire is really what we're concerned with, right? What's that diameter of the wire used to connect the home loads to the transformer? We can do a really easy calculation, right? P equals IV. Power is the product of the voltage and the current. So we can solve for current just by saying I is equal to the power divided by the voltage. So since these loads are in parallel, they both draw 120 volts and they both are 10 kilowatts. So each of the loads is going to be 10 kilowatts divided by that parallel combination, or parallel voltage of 120 volts. So 10,000 divided by 120 is 83.33 amps. And so that means there's 83.33 amps flowing through load 1, and there's also 83.33 amps flowing through load 2. We can then determine total load by adding the sum. That's, again, Kirchhoff's current law. So KCL is going to tell us that the sum of the currents flowing into that node here, which is just I, is going to be I1 plus I2. So I total, we can just calculate, or I total, excuse me, equals I1 plus I2, and so that's just 2 times 83.33, which gives you 167 amps, about. I rounded up, 167 amps. So this wire that connects from that node to that node needs to be capable of handling 167 amps. To serve this load, we'll learn later that we would choose a wire gauge of 1-0. So that's we'll do a section on transmission and distribution wire with a little bit of look at residential wiring gauges. We choose a 1-0. This is a 6 millimeter wire. The diameter of that wire is 6 millimeter. It also weighs about 300 pounds per 1,000 feet. So if I roll out 1,000 feet of this wire and were to lift that up, that's 300 pounds. One way to reduce the need for this wire is to increase the voltage at this voltage source, and then to redesign the loads such that they operate at a higher voltage. I'm going to show an example of that circuit. So if this were lighting, I'm still wanting 10 kilowatts of output power from each of these lights, but instead of serving it with a 120 volt load or 120 volt source, I'm going to now serve it with a 240 volt. What does that do to this current draw? So again, we just divide the 10 kilowatts. This time, instead of dividing by 240, we divide, or instead of dividing by 120, we divide by 240. So not too surprisingly, that's going to drop our current in half. We get I equals P over V. That's 10 kilowatts over 240 volts. And you do that math and you get half what the previous calculation was, so you get 41.67 amps of current in each of these branches for a total current flow of 83.33 amps. .33 amps. So total current is also half of what was required in the previous example just by increasing that voltage. Since that total current draw is halved, we can get by with a much smaller wire. In this case, we would look up at the tables and we would find out that this needs 4-gauge wire, and 4-gauge wire only weighs about 150 pounds per 1,000 feet. So I need much lighter duty utility poles to hold the wire in this case, even though I've been using a higher voltage. This example shows one reason why power distribution systems engineers prefer to use high voltages. We can reduce the capital cost by the use of smaller, lighter, cheaper wires and the supporting infrastructure. The disadvantage is that this higher voltage is going to place customers in just a little bit more of danger due to an increased risk of electric shock, and then also, if the devices not constant power. For example, if this was a resistive load, this would draw more current, right, and the power would go up. So these devices really do have to be designed to operate at that supply voltage. I couldn't just simply take something that was designed at 120 and operate it at 240. Right. For example, the majority of the power systems in Europe are actually designed at 240, which is why I chose this example. And the purpose of that is to reduce current loads. If you take an American appliance, such as a blender, a toaster, a hair dryer, an electric shaver, or anything like that, and you try to plug it into a European outlet, well, you're going to fry the device because it was designed to work at 120 and it's going to pull more current. So it does actually require a redesign of the end devices. Have no fear though, you could use a step-down transformer to convert that 240 down to 120, and then your appliances should work just fine if you were to travel to Europe. But they do, the two systems, the European system using 240 and the American system using 120, they really are operating at different voltage levels. There is kind of some corrective action that we can take in that situation, though, to improve the system while using the devices that we currently have. Let's look at what happens if we place the loads in series while keeping the 240 volt supply. So assuming that these both are equal power draw, 10 kilowatts here and 10 kilowatts here, 120 volts is going to get dropped across each of the loads due to the voltage divider. And the total current sourced by the 240 volt source is still only going to be 83.33 amps flowing through the load, combines load. In this configuration, even though the 240 volts exists across the terminals of the output terminals of the transformer, the individual loads, when I measure from here to here and from here to here, if I were to take either of those measurements, the individual loads are only going to see 120 volts due to their series configuration. You guys probably are already screaming there's an obvious fault with this circuit. If these represent loads in the home, for either of them to work, they both would have to be turned on. If I were to disconnect this load by flipping a switch or disconnect this load by flipping a switch, I would in essence be turning them both off, right? If either load is switched off, current in the circuit will not flow and both circuits are going to turn off. So there's an obvious problem with this. I can modify it though briefly by adding a third wire to it and then splitting the voltage into two separate supplies to address those issues. So here you can see I've got a 120 volt source at angle 0. I've got a second 120 volt source at angle 0, right? These voltage sources are in phase. Since they're in phase, vector addition would just be 240 at angle 0, would be the total voltage supplied by that. And then we've added this third wire, which in this case we're going to call the neutral. These two wires, the 120 volts, are supplied in phase, are wired in series to produce 240 volts, and the third wire is run to the connection point between the loads and the generators to allow either of the loads to open. We can see with the addition of this wire, if this load's open, this bottom circuit still has a return path, and if this load's open, this top circuit still has a return path. Excuse me, if this one's open, this can still operate. If this one's open, this can still operate. Right? This design is relatively common. It's called split phase, or sometimes called a split phase power system. You can use 3 smaller wires. It's more expensive than the 2-wire system we just showed, but it's still cheaper than the 2 wires needed in our original 120 volt design, and the risk to shock at a customer who would be located at one of the connections to the supply at an actual electrical device, you know, where the customer is actually plugging his electrical device into the plug, it's low because it's down to 120 volts. So an additional interesting fact is that this guy's going to draw 83.33 amps. This guy's going to draw 83.33 amps, but due to the loop configuration, currents flowing in this loop here and currents flowing in this loop here, in the neutral wire, the 83.33 loop flow on the top circuit and the 83.33 amps of loop flow on the bottom circuit are actually going to cancel. So the neutral wire, what we would say more generally is that it only has to carry the difference between the 2 load currents. And in the case that the loads are perfectly balanced, as we've illustrated here, the neutral wire will always carry 0 current. So split phase, I get the benefits of the reduced current due to the higher voltages, carrying 83.3 and 83.33 here. That's the total current in either branch. And because of the subtractive nature of the middle branch, I never carry twice that current value like I did in the original single phase 120 volt supply. So I get the benefit of reduced current flows in the wires. In practice, most American homes are actually supplied by this method. Lighting and small appliances are going to be connected between a live wire, either the top or bottom of the circuit, and the neutral. So that might represent a light bulb. This might represent a television. Large appliances such as cooking equipment, space heating, clothes dryers, things like that, washing machines, they're going to be connected across the 2 live wires. And what we can see is that connecting across the 2 live wires is going to supply 120 volts. How this is achieved in the US is through the use of what's called a center tapped utility transformer. In this diagram, we see that we've got an input voltage at 2.4 kV. We've got a transformer. Unlike the transformer diagrams that you may already be familiar with, this one has 3 connections, that middle connection being called the center tap. And what we can see is that by center tapping the transformer, which basically is just dividing this coil in half, I've created 2 120 volt circuits. If I ignore the center tap and connect across the output terminals of the step-down coil, I get 240 volts. And these are all coming off one transformer phase. That means 120, 120, and 240 volts. Those are all in phase, right? They're all in phase. So the resultant name of this circuit is 120 single phase, 240 single phase, 120, 240. a lot of times people will call it. But it's 120 single phase, 240 single phase. The voltages are in phase with one another. Schematically, a lot of times you'll see this representation right here. It is two sources that are 180 degrees out of phase. So if I've got a voltage source, its positive terminal pointing up in this case, and I've got a second one with its positive terminal pointing down, we would call that 120 at angle 180. And what that does is it causes a vector addition of those two voltages to sum up to 240 angle 0. You would do 120 angle 0 minus 120 at angle 180. That gives you 240 at angle 0 if you were to use KVL around the closed loop for this 120-240 volt circuit. So if you were curious about the residential wiring in your home that you typically have access to for your lighting or small appliances or for your dryer, this is actually how the home is being served. One transformer will usually provide electricity to just one home, and then these two circuits will be balanced typically. Right? You'll have some appliances running off this circuit, you'll have some appliances running off this circuit, and then you'll have additional appliances running off you'll have your washing machine, dryer, and things like that. So you'll basically have three different circuits running in your home electrical system. So to connect that to your wall outlets, what does that look like? Well, here what I have is kind of a stylized picture of the standard wall outlet in the United States depicting the three connections, blue, red, and green connections. Modern outlets have three connections, or safety plugs have three connections. Older outlets a lot of times only have two connections, and a lot of appliances have two plugs, while some appliances have three plugs. So what's going on with this? What's actually the arrangement of these plugs? What's necessary, what's not necessary? So this diagram here is depicting the connection that's standard for the United States. First, what we have is the red. This is the hot wire. It's supplying 120 volts RMS plus or minus 5%. That's US standard voltage tolerance, as measured to the neutral wire. So I'm using the neutral wire here as my reference. That one's 120 volts RMS. Neutral's the return wire and should be at 0 volts, but will float 1 to 2 volts depending on how well the loads on the separate phases are actually balanced. The ground, which is called the earth, also is intended to connect physically to the earth, which is typically achieved by connecting to the water pipes in a building, and its purpose is to prevent shock hazard. This is really achieved by connecting the ground wire inside of an appliance to the plug that would plug into this. If for some reason the hot end of the appliance would come into contact with a metal chassis on the device, a high fault current would then flow to the ground, to the earth ground, since this thing is also connected to the chassis. So that would in essence be a hot to ground short, causing a high fault current. And then your circuit breaker in your home, your fusing device, or whatever your protective device is, should trip. So just to put this in context of this previous diagram, red and blue, or red and blue, depending on how it's which of the phase it's connected to. And then this terminal is actually not even depicted electrically in this, since it's the earth ground, which is different than the neutral in this case.